This lesson will be about sequences and the formal definition of a limit. So the first thing we'll do is define what a sequence is. And it's really simple. You can just think of a sequence as a list of numbers. The list that I'll use is this one. And of course it could continue. So this would be the first term, second term, third term, nth term, and then on. So they could be in numerical order or not, or they could be determined by a formula. So all that will be determined by the specific sequence. One example is, I don't need to list it like that. So if that is a sequence, we could write a formula for the nth term. So maybe it's a good idea to hit pause on the video and see if you can construct a formula for whatever the nth term is out here. So why don't you go ahead and do that now. Okay, so here we are then. Hopefully you saw that the sign changes back and forth. A little device to change the sign back and forth is -1 raised to the nth power. If I leave it as to the nth power, that would mean the first term would be negative because it would be -1 to the first. So I'll just make it -1 to the n-1 power. So now it'll be -1 to the 0th power makes it positive. The second term will have -1 to the 2-1, which is the first power, so that'll make it negative, etc. So that will control our positivity and negativity. And then from there, the top of our fraction looks like n plus 2 over 5 to the n. N plus 2 over 5 to the n. So the first term would be 1 plus 2 is 3. The second term, 2 plus 2 is 4, etc. And the bottom you can see is going up by 5 to the n. So anyway, this would be a sequence, and we would call this guy a general term. The a sub n would be the general term of the sequence because it finds you somewhere along that sequence, it'll find you the term. So if you wanted to know the 75th term, you could just plug it in there. I would know just by looking at this, the 75th term would be positive. But anyway, so enough about that. Now, the limit of the sequence if we say, if a sequence has limit L, then we say this. Limit as n approaches infinity of the sequence a sub n is equal to L. So in other words, if we were to take this list and just follow it all the way out to the 10 billionth term, what is this sequence getting closer and closer and closer to? This one, you might see the denominator is exploding, the numerator is just getting slightly bigger. So this one's going to get closer and closer to 0. But it's really, at this level of mathematics, is not enough to say, oh, what's going to get closer and closer to? So we're going to very rigorously define what does it mean to get closer and closer to a certain number. So that rigorous definition of a limit, you need to see two set theoretical notations prior to going through this. They look a little funny, but they're pretty simple. When you see this little guy, this means for all. And if you see this little friend here, he means exists. So yes, it is an upside down A, and yes, a backwards E. You're going to see something that looks a little bit strange on its face, but just give it a second and it'll make a lot more sense And by the way, if you don't prefer this kind of notation, then just don't use it. Just write the word for all and write the word exists. But knowing the level of class you're in at your age, it might be something, as you head down the road in math that you'll see these again anyway, so you might as well get used to the language now. So the rigorous definition of the limit, rather than just simply saying this, we need to define what that means. The definition is as follows. The limit as n approaches infinity of the sequence a sub n is equal to L if, for all epsilon's greater than 0, and I should say epsilon could be any real number. Epsilon is an element of the reals. For every epsilon that one chooses, there exists an n, which is a positive integer, such that if I choose some little n bigger than the big N, then the sequence minus the proposed limit will be less than epsilon. So that, that's that. I'm sure you understand it now. Probably not. So let's think about it. If epsilon is greater than 0, think about this kind of as like an epsilon game. So somebody says, if you think the limit of your sequence is 5, they say, well, I want you to show me a term that is within 0.00001 of 5. So if you go way out in your sequence, you should be able to produce a term that's like 5.000000003, because that would have been within the defined accuracy. Let's say they wanted to be within 1/1000th. So that would be the named epsilon. What your job to do, the onus is on you as the prover here to show the person who's saying, well, can you get this close? Can you get within 1/1000th? Your job is to show them that no matter what number they name for epsilon, you can produce the certain term that they would have to go to. So if they said, oh, I want it within 1/1000th, you could say, oh, go to the 37th term and you're fine. Or if they said, I want it within 1/1,000,000th, you should be able to say, well, go actually this time to the 63rd term, and that will get you within 1/1,000,000th. But in general, we can't play this game all day. So what we need to do is be able to take a general epsilon and produce some n value such that when you're past that n value, when you're past the 63rd term, and you're at the 64th, 5th, 6th, now it's guaranteed that if I take the sequence, the value of that term, subtract out the proposed limit, I'll be guaranteed to be epsilon close to that value. So at the end of the day, we need to have n in terms of epsilon in order to prove that the limit is whatever we said it was. Okay, that probably isn't totally clear. So we're going to do an example. But remember, just kind of think of it as a game. You're provided with an epsilon, and your goal is to, no matter what that epsilon is, show that person that you can produce a proper n value that will get them within epsilon of the proposed limit. So let's look at this sequence. Hopefully it is clear that the limit of this sequence, well, think about it for a second. As n approaches infinity, limit of the sequence should be 0. So our L value is going to be 0 here. That's where I'm saying, hey, the limit is 0. And if you're wondering why, this will be some big number over some much bigger number plus 1 as n goes to infinity. And if the denominator is smaller than the numerator, of course, the denominator is dominant, and then we get 0. So we should be able to then prove this. So we're going to prove that the limit is 0. And our proof will start by considering excuse me, if the nth term of our sequence minus 0, right, I'm in this form, is less than epsilon. If that's the case, then just filling in for a sub n, I took out the 0 because minus 0, of course, you get 0. Now we have positive n's here because n is going to positive infinity, so I'm just going to get rid of the absolute value. If you're wondering where the absolute value comes from in the first place, if you want to know the distance between two numbers or how far apart they are, you subtract them and you take their absolute value. That way you don't have to worry about which one was bigger in the first place. Okay, now here's where the crux of this proof comes in. We need to somehow get n in terms of epsilon. So for example, maybe at the end of the day we'd say, oh, n is less than 2 epsilon. That is not true for this problem, but let's just say n is less than 2 epsilon. What that is there to say is that if somebody names, I'm sorry, that wouldn't make any sense. N is greater than 2 epsilon. If somebody names an epsilon, let's say their epsilon is 1/1,000,000th, you could say, oh, I want your nth term to be 2 times that, just needs to be greater than 2 times that epsilon. A little bit of a strange numerical example I provided you there. But we'll see how this works. But the problem is getting this thing, getting n in terms of epsilon, like n greater than some function of epsilon, is a little strange here. So you need to take this thing and somehow simplify it a bit. And what we're going to do is actually compare it to something else. And that something else is going to be n over n squared. So side note here, n over n squared plus 1 is smaller than n over n squared. If you're wondering why that's the case, well, if a numerator gets smaller, then the fraction is necessarily bigger, given that everything is positive. So if that's the case, and that thing is equal to, of course, 1 over n. So if this guy is less than 1 over n, all I would have to do is name my n value in terms of epsilon relative to 1 over n, and then I will have necessarily provided a value that works for this one. So we're going to set that less than epsilon, because if that is less than that, and that is less than epsilon, then the game's over. And if this is true, if and only if n is greater than 1 over epsilon. So this now is going to be our special value of n that we choose given a certain epsilon. If you want to, I guess, like in terms of IB, you need to be able to do this process, get n's in terms of epsilon, and then afterwards you need to make some sort of reasoning statement where you say, okay, now I've shown that given epsilon, so given epsilon greater than 0, there exists an integer n greater than or equal to 1 over epsilon such that a sub n minus 0 is less than epsilon, which establishes the limit. And if you're wondering, like, how in the world does this actually work? Well, actually take an epsilon value, name yourself an epsilon value, such as I want to be within 1/100th of 0, so if 0 is the proposed limit. Take that value and plug it in, choose your n, and then use that nth term to see how close you can get. Okay, we're going to resume study of limits, but that's it for the formal definition.